In this module, I'm going to go through a very detailed case study. This case study is from my research to introduce all the aspects of reliability that I mentioned in the previous module 1.1. So this is a case study on fatigue failure in solder joints in electronic assemblies. Electronic assemblies, a component on a circuit board, typically goes through thermal cycles, by which I mean that every time you switch on your computer or your electronic device, the chips heat up, and then when you switch it off, the chips cool down. And because the materials in the assembly, the chips, have very low thermal expansion coefficient, and the components have the circuit boards have larger thermal expansion coefficients. As a result, you have differential expansion between the component and the circuit board. And if you do this enough number of times, eventually you initiate a crack in the solder joint, the assembly that holds together the component on one side, the circuit board on the other side. You initiate a crack, and as you cycle, the crack starts to propagate, that you can see here. And eventually, the crack runs through the entire solder joint and breaks the solder joint, which time you don't have electrical connection as well as mechanical support. Solder joint also performs the function of removing heat. So it performs three functions. It provides electrical connection, mechanical support, and a heat removal path. So from the chip onto the circuit board, through some copper planes in the circuit board to external sources. So solder joint performs multiple functions, and it's critical. So therefore, equipment manufacturers or chip manufacturers like Intel spend an enormous amount of time characterizing solder joints. And this particular study was, in my case, was funded by a consortium of electronic companies called High Density Packaging Users Group. This was done about 20 years ago. And this consortium at that time included companies like HP, Sun Microsystems, which is now part of Oracle, and other companies. Later, we did another study, and this was in collaboration with Texas Instruments. So this is a different kind of a solder joint. Again, solder joint attaching a component to the circuit board. It's a different kind of a solder joint. And again, you see similar phenomena. Crack initiates, the crack grows. When the crack has gone through the joint, you've broken the electrical connection as well as the mechanical and thermal pathways. So this is what is called a quad flat no lead QFN package, and this basically determines how the connections are made between the component and the circuit board. This is a ceramic ball grid array component. It's a CBGA, stands for ceramic ball grid array. There were 483 solder joints on that package and 64 in this particular package, and they were thermal cycled from 0 to 100 degrees C, and this is from minus 40 to plus 125 C. And these conditions depend on the intended use environment of your product. So for office use, 0 to 100 degrees C is a typical test condition. More aggressive use, you might have minus 40 to plus 125. If it is in avionics, you might couple temperature cycling with random vibration. So the approach that we used in the study is it's actually both experimentation coupled with modeling. For modeling, we independently characterize the material of the solder. So this material we characterize independently in mechanical tests, elaborate mechanical tests, and those are the kinds of behavior you'll get. Build a constitutive model which describes the stress-strain response of the material. And then we develop failure models and do failure experiments, compare the failure models to the failure experiments. The failure models describe what the expected life would be or how a crack would grow given a stress state. So incrementally, at a given stress, how quickly the crack would grow. And then you compare your predicted crack against the actual experimentally observed crack. So how did we do the experiments, the failure experiments? There are many failure tests one can do to electronics. Accelerated thermal cycling is by far the most common. What you do is you take a circuit board wired to identify electrically when a solder joint has failed electrically. And then you stick the circuit board in a thermal oven, cycle it between whatever temperature range. Then you have something called a simulated power cycling, where you don't stick circuit board into a big oven, because in the big oven you're actually spending a lot of time heating the air around the component, and the component itself is very small. So the simulated power cycling is basically a localized heating on the component. You don't stick the whole board into an oven, you locally heat a component, and that's much quicker than thermal cycling in a oven, simply because you don't have to heat up the air. So you're just locally heating on the chip. And some argue that's more appropriate simply because chips heat up in real use, and this is more representative of real use. So power cycling, you actually have chips that are heating up and cooling. If you have a cell phone or a tablet, you might have to do drop test as well, because that's a drop is a very common failure cause. And you might have to do vibration as well. And failure analysis might require cross-section, dye and pry, X-ray. Okay, this is acoustic microscopy to see if there is delamination inside. These are all possible tests. What we did in our case was a simulated power cycling, and we had a thermoelectric device, a Peltier device, which was which was bonded onto the component. That's the component, and this is the circuit board. The green part is the circuit board and solder joints in between. So the Peltier was connected to the Peltier device. The thermoelectric device was connected to the component. This Peltier device, when you supply current to it, it heats up, or it can also cool down. If you reverse polarity, you can cool down. And since Peltiers are not as efficient while cooling, so we also attached a water-cooled heat sink to remove the heat. And this is the temperature profile that we were trying to simulate. So we wanted to go from 0 degrees to 100 degrees C, hold for some period of time, 10 minutes hot dwell, and 10 minutes cold dwell. This is the temperature profile that you would see in an oven, but what we achieve through careful control with the Peltier device, it's not quite exactly the same as an oven, but this is the kind of profile that we achieved with the Peltier device. And this is when you do these tests on lots and lots of components, we had 30 plus components. And when you do them, you get this sort of a failure time, which you plot on a specific, in this particular case, we used Weibull distribution to characterize the failures. And then you can ask the question, is Weibull the best distribution to characterize these failures? Can I come up with alternative failure distributions? And the answer is yes. But Weibull is very popular in industry, and that's why we used Weibull. So we compared 10-minute dwell versus 30-minute dwell versus 60-minute dwell for the two alloys that we were characterizing. So the goal was for these consortium members to figure out the difference between these two alloys. Originally, SAC 387 or tin 3.8, 0.7 copper, tin 3.8 silver, 0.7 copper was popular. But then a new alloy was found to be better for some applications. There was tin 3.0 silver, 0.5 copper, and the industry wanted to understand the difference between the behaviors of the two alloys, and that's why we did these tests. And then, as I described in module 1.1, we did post-failure analysis. Now I'm going to talk about failure models. So there are common empirical fatigue failure models called Coffin-Manson for low cycle fatigue. And we will learn about these very briefly towards the end of the course. So in general, when you have low cycle fatigue, meaning failures occur in less than, say, 10,000 cycles, then the components must, whatever is failing, must undergo large plastic deformation. Metal part must undergo large plastic deformation. And therefore, plastic strain range over which you cycle the part is a good indicator of how long the part will last. So the N sub F is number of cycles to failure. And you can correlate empirically number of cycles to failure to the reciprocal of plastic strain range raised to some parameter m. And this m is typically 0.5 or delta epsilon to the power 2. And this doesn't account for the cycling frequency, so therefore there's a frequency modified Coffin-Manson relationship. These are all traditional fatigue modeling methods. This is not what we used, but this is how typically people model them. And our belief was that this is not a very good way to model because these are empirical. These are not actually following the crack growth process, and therefore their predictions are pretty poor. They're often in fatigue, you will have errors of 100%. So typical traditional empirical life estimation methods are once you have done your cycling test, once you've estimated the number of cycles to failure, then you would figure out an acceleration factor which predicts how long that same product would last in field use environment. If it lasts, say, 100 cycles under accelerated test conditions, how long would it last in field use environment? And we use acceleration factors. We'll predict acceleration factors since in our case we are accelerating primarily by temperature, by looking at temperature in field use environment relative to temperature under test conditions. We can predict how long the same part will last in the field use conditions. There are these various acceleration factors. We will learn in detail how to estimate these acceleration factors in this course. The approach we used is more similar to the approach that I'm showing you here. And I'm going to skip this slide and move forward and explain that pictorially. When you stress any point in the material and you cycle it over a range, the material is actually, you're actually putting an energy into the solder joint at every point in the material. And when you cycle, you actually dissipate some energy because the material is undergoing nonlinear response. Because of this nonlinearity, the load path is different from the unload path. And as a result, every time you cycle, you're losing some amount of energy. This energy goes to damage the solder joint, which eventually leads to crack initiation and crack growth, which is what we're trying to model. And this, again, you can come up with an empirical model where instead of strain range, you look at dissipation per cycle, delta W, dissipation per cycle. And this is how to estimate this is not clear. And it's very package construction geometry dependent because it's an empirical fit. It's a curve fit. So we wanted to try to come up with a more physics-based approach. So what we said is, as a first step, what we said was, let at every point in the material, let the failure be described as a Weibull distribution. Okay, we will learn this in detail in this class. And then if I track the points where the material has failed, the loci of the points where the material has failed will give me the crack front. And we used that to predict the crack front progressively as the cycling went on and compared it to the crack front that we observed experimentally, and they matched very well within 20%, which is actually very good. This is for tin lead solder. And later, we were characterizing tin silver copper solder alloys, and it turns out tin silver copper solder alloys have very few grains in them. If you take cross section in solder joint, you'll find very few grains in them because tin tends to grow, and it's primarily tin. There are very few tin grains in a solder joint because of what's called tin undercooling. So there's a fair amount of microstructural uncertainty because of the fact that there are very few grains in these tin-based solder joint. So we came up with physics-based theory, which we called as max entropy fracture model. And this is accounting for thermodynamically the entropic dissipation, and what it's attempting to do is to maximally be non-committal to microstructural uncertainty. So it's basically developing, I'm going to go through this somewhat quickly. So in any fracture process, there is inherent uncertainty in the length scale, meaning that the cracks don't look the same at all length scales. At the largest length scale, or if I zoom out, I see a crack going across the interface. If I zoom in, I see more jaggedness to the crack front. However, at the larger length scale, there is predictability. So there is an inherent hierarchy in fracture process. And while it might seem uncertain at the local length scale, at the larger length scale, it is predictable. So that sort of uncertainty can be characterized using theory, information hierarchy. And what that predicts is that a material at any point would accumulate damage according to this distribution. And this is actually an exponential type distribution. And then this particular model is inspired by theory of statistical mechanics, physics, thermodynamics. And so this W here is dissipation, and K is some parameter that's inspired by Boltzmann distribution, Boltzmann constant. And it turns out that K can be extracted. That's the single parameter that predicts how fast or how slow the crack would grow. You can extract that by isothermal mechanical tests in the lab, which is what we did. This was a student's PhD thesis, the student. So we would characterize basically the load drop from the first cycle to the last cycle. We would characterize the load drop and then estimate that parameter K. Now we went and did independent thermal cycling experiments on a package, on a real package. So far, all the tests were done on a sample. The sample is different from a real package, and these were at isothermal conditions. So then we go do tests on a real package, and this is a package that we tested was from a company called National Semiconductor, which is now part of Texas Instruments. So we take a wafer level chip scale package, and then we cycle them in a thermal chamber. And every 240 cycles, the test board was sent to us to do failure analysis. So we characterize how fast the cracks grew in the real sample. Every 240 cycles, they were sent to us, and we characterized them. And this is the growth of the crack. This is how far the crack had grown at that number of cycles. You can see that the crack growth is not linear. It's highly nonlinear. So this is the normalized crack length. This is the number of cycles. It's highly nonlinear. So now we applied our max entropy fracture model to predict the crack. Now in the max entropy fracture model, we obtained the failure description was developed using isothermal tests. So the model does not have any data derived from the thermal cycling experiments. And here's a damage accumulated at a certain number of cycles. You can see that different joints on the package accumulate cracks at different rates, as you would expect, because they're all stressed differently. And on the critical joint, the corner joint, you can see the crack growth as predicted by the model. And of course, the model is independent of the thermal cycling experiments on the real product. And you can compare the model prediction crack growth to the experiments. It's actually quite reasonable. And finally, if you look at the crack front, they compare very well within 10%, which is usually very, very good for fatigue prediction. So the key point of this case study is that you would need to do, in order for you to characterize life, you need to take a sample, cycle them, test them to failure, and then you need to study the physics to develop a model. In order for you to be able to do detailed failure prediction, you need physics. And that's the part we will not cover in great detail in this course. However, both are important. I want to leave with that message that both are equally important. So with that, I'm going to stop this particular module.